In this podcast, we'll be going over valence bond theory and how valence bond theory explains bonding for covalently bonded molecules. So if you recall, VSEPR theory, even though it was very successful in explaining the 3D molecular structure of covalently bonded substances, it could not explain the bonding in terms of bond strength. Valence bond theory provides a basis for covalent bond formation by assuming the overlap of atomic orbitals. When atomic orbitals overlap, the shared electrons are attracted by the nuclei of the atoms that are sharing the electrons, resulting in formation of a covalent bond. The highlight of valence bond theory is that this theory successfully predicts the bond strength and bond length in terms of orbital overlap. For example, hydrogen bond strength versus nitrogen bond strength. Valence bond theory says that nitrogen bond strength will be greater than hydrogen bond because nitrogen bond is triple bonded while hydrogen bond is only single bond. And triple bond, because of presence of three bonds, greater overlapping, more sharing of electron, higher electrostatic forces, is stronger as compared to hydrogen bond. Now let's take a deeper look at valence bond theory and how it explains covalent bonding. So valence bond theory is all about overlapping atomic orbitals, and then the shared electrons are attracted by the nuclei of the atoms that are sharing these electrons. There are three basic principles of valence bond theory that are in accordance with, just a second, let me go back here. I'm sorry, let me start again here. So the valence bond theory has three basic principles. The first principle says that as atomic orbitals overlap to share their electrons, the shared electrons must have opposing spins of electron pair. And this goes in accordance with Pauli's exclusion principle. You remember Pauli's exclusion principle had stated that if two electrons are present within the same orbital, then they must have opposite spin if the atom is stable. Because if their spins are in the same direction, it will generate an electric and magnetic field. They'll not cancel each other, and then the atom will become unstable. So valence bond theory says when the atomic orbitals of atoms overlap and electrons are shared, the shared electron spins are in opposite directions, so they can cancel the electric magnetic field generated cause of their spin. The second postulate of valence bond theory says that the more the overlapping of the bonding orbitals, the stronger the bond is. So if there are two atomic orbitals overlapping, then there will be the stronger bond. The third postulate of valence bond theory is that there are different types of overlap of atomic orbitals which result in different type of bonds. So there are mainly two types of bonds, sigma bonds and pi bonds. Sigma bonds are formed by overlap along the internuclear axis. So if this is atom A and this is atom B, any overlap between atomic orbital along the internuclear axis will form a sigma bond. This is abbreviation for sigma, while any overlap of p orbitals along y-axis or along z-axis will produce a pi bond. And we'll look at sigma and pi bonds more in detail in the next slide. So sigma bonds can be formed between hybridized orbitals or unhybridized s, p, d, or f orbitals. The only condition for a sigma bond is it needs to be along internuclear axis. And because it is along the internuclear axis, there is enough space for a good overlap between the atomic orbitals. So the sigma bond is fairly strong. Every single bond is a sigma bond. A pi bond is a specific type of bond that's formed by side-by-side overlap of only unhybridized p orbital. So not every orbital overlap produces a pi bond. A pi bond is formed only between overlap of py or pz orbital along the y-axis overlap or along the z-axis overlap. And as you can see here, this overlap is not that much. There's only little overlap along the y or z axis, hence the pi bond is not quite as strong as the sigma bond. In multiple bond situation, the second and third bonds are always pi bonds. Again, to just convey this point, sigma bonds are always the first single bonds. Pi bonds are the second and third bonds in a double or triple bonds. Now, how does covalent bonding as for valence bond theory happens at the atomic level? So if we were to look at formation of a hydrogen molecule where two hydrogen atoms are approaching each other with a possible overlap, and we have drawn a graph here between the changes in energy and the distance between the two hydrogen atoms. We are talking about the interatomic distance. How does the distance between the nuclei of two hydrogen atoms that want to overlap their orbitals change, and how do the energy changes occur as this overlap is happening in this graph? So you can see when the two hydrogen atoms are far from each other, like in A, then the energy is fairly high because there is very little force of attraction between them. Before we get into studying the energy changes with the two atoms approaching, let's get one thing clear. Attractive forces in chemistry mean lowering of energy, and repulsive forces in chemistry mean increase in energy. So as the atoms are approaching each other and there's attraction between these atoms, because attractive forces correspond to lowering of energy, you can see from A to B energy is starting to lower. So that indicates that now the two atoms are starting to attract each other, and as they go towards each other there is overlap of their atomic orbitals, and the electrons that are in these overlapped atomic orbital, they are attracted by the nuclei of the two atoms, which causes a force of attraction and a lowering of energy. As the overlap becomes even greater or the atoms approach even closer, that's represented by the area BC here, there is greater attractive force for these shared electrons by the nuclei, and energy further lowers. And now if we look at part C, where the distance between the two hydrogen atoms is 0.74 angstrom, you will see that this is indicating the lowest attractive force. This is the lowest energy because of the maximum electrostatic attraction. At this point, the attractive and repulsive forces are balanced. This is the lowest energy state, hence the most stable state, and we call point C as the bonded state. Because if the atoms come any closer than 0.74 angstrom, then the energy again starts increasing due to increased repulsive forces between the proton and protons of the two nuclei. So there is that fine balance between the attractive forces between the protons in the nucleus and the electrons, and the protons in the two nuclei of the atoms. And whichever place this attractive and repulsive forces are balanced and there's lowest amount of energy, we call it as the bonded state. For hydrogen molecule, the bonded state occurs when the two hydrogen atoms, the internuclear distance between them is 0.74 angstrom. Even though valence bond theory was very successful in explaining the bonding in terms of overlapping of atomic orbitals, sharing of electrons, and attraction of electrons by two nuclei, it could not The biggest limitation of valence bond theory is it assumes that all the shared electrons are always localized. However, that is not true. A lot of the bonding happens because of delocalized electrons, and valence bond theory does not regard those. That is one shortcoming of valence bond theory. Hence, the most current theory that we use is called molecular orbital theory, which takes into account the delocalized orbitals as well. And that is the end of the podcast. Thank you for listening.